There are other rather more exotic particles you can talk about. There's ideas of say WIMP-zillas. These are supermassive particles that are actually almost macroscopic. They sort of weigh micrograms, but they would be very, very dispersed through the universe. Or primordial black holes is another possible way of suggesting that this dark matter may be composed. Or there's a particle called an axion, which actually I shouldn't be too cheeky about, because actually it's almost as good a theory as this one. But there are many different theories for what this particle dark matter or this dark matter may be. But right now, this is the one that we're putting most of our eggs in the basket, just because it still, after all this time, seems to be very well motivated. And one of the ways we might actually get to create it in the next 5 years, if we don't, as I'll show you with our experiments, see it directly by detecting it, maybe we can actually create it. And this thing here is the Atlas detector, and it's on this ring in Geneva, on the border of Switzerland and France, which is 27 kilometers round. There's a beam pipe coming in this direction, and there's a beam pipe coming in this direction. Now, for those of you that haven't seen it yet, to give you an idea of the scale of this experiment, those are the people. And this really is to scale. This is huge. They have really excelled this time. Some of the previous experiments were big. This is just one detector. There are 4 of these guys around this ring. This is truly monumental. There's another person there. So it's just the beam pipe interaction. The beam pipe is, sort of just a few centimeters across. These protons are coming around, at light velocity, very high energies. But every time they collide, they just create, this thing lights up like a Christmas tree. It's incredible. And the data rates, the data flows coming out of this immense machine are truly fantastic when it's working. And it has to do this repeatedly, billions of times a second. And what they're going to be doing is building up statistics to see whether they can see evidence for the creation of new particles. We already know with conventional physics a lot of stuff is going to be created. We really don't care about that. We want to know about the new stuff. So you have to filter through all this conventional stuff. But the reason why this is a good bet is because this is much higher energy than anything we've previously built. And energy in particle physics is all about energy. So that's the ring at Geneva, 27 kilometers round. But anyway, I should. Oh, sorry. Hi.
The tunnel is about 20 feet, containing a ring which is approached, and the magnets within the ring are what, 10 feet in diameter? I'm guessing.
Yes.
And so that's it's not all in that scale.
No, that is just one of that's the Atlas detector. Okay. I think over there. Okay. So this is just one of 4 detectors that are at of the order of this scale. But the rest of the 27 kilometer guy is just much more modest beam pipe with
it's 50 feet down or something like that.
100 meters. 100 meters. It turns out it's if you accelerate particles in a straight line, that's fine, but we want to reuse the particles, which is why we send them in a ring. Unfortunately, every time you change their direction, they send out a radiation beam, synchrotron radiation, a bit like car headlights, if you like, as you're going around it. You want to bury this ring down at sort of 100 meters so that nobody gets caught in the headlights as you're going round.
Keep the neighbors happy.
Well, it's incredible. The amount of energy in the beam that is being circulated round. I still cannot believe this is true, but it is, apparently. If we were to take a kiloton, 1,000 tons of material, and we were to hoist it up 100 meters, and we were to drop it back down 100 meters, that is the amount of energy that is in just the particle beam. Not in the magnets and all the other mechanical bits, just in the particle beam that is going around this thing. You actually have to be damned careful. Even if we were to let the beam get out of control, it would punch a bloody hole through this detector. We have to make sure it goes down through the pipe. If we get it wrong and steer it off in the wrong direction, it would make it
go through the atmosphere.
Oh yeah, but we don't. I mean, you do not want to be getting people in. The whole point of burying it down 100 meters is
clouds.
Oh, well, that's a cosmic ray physics, yes, you mean. Is that what you mean?
This is part of the-
Weather modification.
Oh, gosh,
Well, after you're finished here,
we better figure out a way of getting unlimited energy before we start that one, because...
after you find or don't
Put it this way,
find those
you cannot, well, sorry, unless they do not run this accelerator in the winter, because the energy bill would be too great. Europe already wants to use its electricity. In the summer there aren't the air conditioners running, so
This is
actually
part
the
of
energy.
CERN, isn't it?
This is CERN, that's right. Okay, so let me just talk about how we're going to directly detect dark matter for a moment. So, if these particles are, sort of on these sort of meandering orbits around our Milky Way, what we're going to do is simply look for the occasional interaction of one of these, and the acronym is WIMP, Weakly Interacting Massive Particle. The mass is of the order of sort of 10 to 100 times the mass of a proton, or 10 to 1,000 times the mass of a proton. And the idea is it just comes through you and I. It's through my hand. There are about sort of 100 million of these, if the theory is correct, 100 million per second going through my hand. Every so often, one of them is going to just bounce off a nucleus. And this is a very key point, which is indeed the signature we are expecting is that it bounces off the sort of nucleus of an atom rather than off an electron. And why that's an interesting distinction is we can build detectors that look for nuclear recoils, interactions where a nucleus gets sort of banged sideways, rather than interactions where an electron gets a kick. Because most radioactive backgrounds in the world are due to electron recoils, not due to nuclear recoils. I really should keep moving on. I'm going to get a terrible time trouble. So, yes, I'm not going to talk about. Sorry, no, I can't talk about this. Let me just. Oh, actually, there is one thing I do want to. Okay, let me do it this way. So, theoretically we have calculated what the probability of these dark matter particles interacting with nuclei is, and the result is not particularly good. I mean, it's been a hell of a challenge, and the challenge is the following: we calculate that, say, in a kilogram of material, so that we fill this with water, that's getting on for a little bit less than actually, but
Close enough.
Close enough. Kilogram. We think the probability, even though there are 100 million or more of these particles coming through this cup as they go on these huge orbits through the Milky Way, we think the event rate may be 1 per month in this cup. Actually, when I started 18 years ago, we used to think it was 100 per day. So that seemed very easy. Actually, I know 100 per day might not seem like very much, but actually to us seemed like an enormous number. So off we went, and we tried to do experiments with things about this size. Actually, things this size, but 100 per day per kilogram seemed very tractable. We didn't see anything, and we went on and on and on, and we're now at the point where we've got, say, something about a kilogram, and we're seeing nothing in it for a month. So we turn to our theories colleagues and say, what the hell's going on? You promised us particles. And they say, oh, well, we've thought about it a bit more. And actually, they are now of the opinion, they're not just making this stuff up, or at least as far as I can tell they aren't. They have strong theoretical, they have strong reason to believe that the interaction rate is somewhere between, 1 per month in this, to say 1 per year per me. Back in the days when I was 100 kilos, which sadly are gone, but maybe even 1 per ton per year. So that's that, and there are reasons why we can't be right now more precise. Until the Large Hadron Collider switches on, and we really hope to start making these particles, we just don't know their properties well enough to pin that down. For theorists, that's a pretty modest uncertainty. I mean, 4 orders of magnitude for 10 to 10,000. I mean, they've been a lot more uncertain than that on some things. So the problem is that